Hello. Today we'll be exploring algae-based biodiesels. Unlike first generation biofuels made from corn or soy, algae is a third generation biofuel. This means that it's derived from aquatic organisms that can grow in places where traditional food crops can't, like wastewater or salty ponds. It's a promising alternative because it can produce significantly more oil per acre than land-based plants. So now the first question that you might have is, how do we grow it? So algae is grown in two main ways. The large open air ponds or closed loop systems called photobioreactors. Through photosynthesis, these algae use sunlight, water, and carbon dioxide to create biomass and lipids that are essentially natural oils. Once harvested, we use a process called transfer esterification to turn those oils into fuel. During the growth phase, the algae perform respiration just like other plants. But the key is their efficiency at converting solar energy into chemical energy. In some other production methods, fermentation is also used to break down the leftover alga scratches into ethanol, ensuring almost nothing goes to waste. So now in the figure we have here, we can see the photobioreactors right here on top that are the closed loop systems, and then we can see the open air pond in the bottom. So now next is our development and carbon footprint. So now algae biofuel is primarily still in its pilot and scale-up stage. While some facilities are producing it, it isn't yet at every gas station. However, its impact on the carbon footprint is incredible. Algae is considered a carbon neutral because it eats carbon dioxide as it grows. In fact, many algae farms are built next to power plants to capture the carbon emission directly. The carbon dioxide released when you eventually burn the fuel is the same carbon dioxide that algae pulled from the air just weeks ago. So now when we look at these two figures on the left, figure two, we have the a graph, and then you can tell the difference of the carbon footprint that's lifted off by each type of fuel that is made. And as we can see, I mean, algae is the best. And then when we look at the other figure, we have the cycle. It's an example of a cycle where what algae can do, how algae takes in carbon dioxide, and how we release it when we use the fuel that's made. So now next is the economics and the public communication of it. So now economically, it's the worst challenge. I mean, it's expensive. It's to produce than petroleum. It's more expensive to produce than petroleum because of the high energy needed to harvest and dry the algae. However, it does create green collar jobs in engineering and biotech. To improve the public perception, the Department of Energy and private companies have launched campaigns highlighting algae as a super crop that doesn't use up our fresh water or farmland. These efforts aim to show the public that we can have fuel security without destroying our food supply. So now when we look at this graph, we can see the different price, like how much more expensive it gets depending on what you're trying to do. And obviously the big orange in each one of those bars is algae, just growing algae, and it's expensive, but in the long term, it can be effective. So now the analysis and the recommendation, I mean, the data that we see, my analysis is that algae is the most technically viable long-term solution, even if it's currently held back by high production costs. My recommendation is to shift our focus forward toward the co-products using the leftover algae to make plastics or animal feed, which would help offset the cost of the fuel itself. We need to move past the research phase and into the industrial size infrastructure. So now here I have made a table right here talking about the pros and the cons. The pros on the left and the cons are on the right. I mean, when we have the pros, we it's high yield. I mean, it's really high yield when we do this. Again, we talked about carbon neutral being the carbon footprint is least, and that's a very good positive thing. And next is the resource efficiency. I mean, these resources you find them anywhere. Saltwater and wastewater too is something that we generate. I mean, we don't generate saltwater, but there's plenty of it in the ocean. Wastewater we generate it with littering and all of these, or we can find, and it preserves our fresh water and the versatility. It can be refined into biodiesel, jet fuel, or even bioplastic. So it has many different things you can do with it. But there are some cons to it. There are some cons. For example, production costs. We have talked about this already. It's expensive. It is expensive to do, but it is worth it. Now the scalability, um, going from small pilot labs to massive industrial ponds, you need to invest. Again, the price is expensive, but it's worth it. And at last, water evaporation. I mean, if it's going to be open air, you're going to have to deal with water evaporation. If we use salt water, you have ocean, so it's fine, but the wastewater, I mean, it will evaporate, but it takes time, more research, we'll find solutions for it. And at last, the plan that I made, if funding was not an obstacle, I would propose the Coastal Carbon Capture Initiative. We would build a massive network of photobioreactors along every major coastline using that salt water. And these photobioreactors will be powered by offshore wind to treat the municipal wastewater while simultaneously providing 100% of our aviation fuel needed. This would turn our waste into energy on a global scale. This is the end. Thank you for watching, and here are my references for the project. Thank you again.